the integral of 1 over t times, not parentheses, 2 over t squared minus 3 over t to the cube.
Okay. So we always have to undo products and we have to undo quotients. So let me do the product first. I'm going to send the 1 over t through the parentheses. And when you multiply like bases, you add the exponents. So we'll get 2 over t cubed minus 3 over t to the 4th. Now the next step is to move the t's up and write them with negative exponents. So we have 2t to the negative 3 minus 3t to the negative 4. And now we're ready to integrate. Term by term, hold the constant, add 1 to the power, divide by the new power. So when we're in here, we add 1 to the negative 3. Negative 3 plus 1 gives us a negative 2. So I got t to the negative 2 divided by negative 2. Here's the 2 from the coefficient, and there's the negative 2 from the power rule. All right, so next we pull out the negative 3, add 1 to the power. Negative 4 plus 1 is negative 3, and then we divide by that negative 3. Done the antiderivative, so we tack on a plus c, the rest is simplified. I'm going to cancel the 3's and the 2's and the minus signs, and I'm going to put the t's on the bottom. So this becomes a negative 1 t to the negative 2, which is negative 1 over t squared. That becomes a positive 1 t to the negative 3, so that's plus 1 over t cubed. Okay? Get rid of products and get rid of quotients, best that you can.
So never use the product or quotient.
We don't have a product or quotient rule for integrals. We don't have anything of that ilk. Because think how many different ways a quotient rule can be simplified. It'd be hard to recognize what quotient we took the derivative of to get this simplified thing. Same thing with the product rule. Any more?
That's all I have.
Okay, I put a review sheet on Blackboard outlining what we're doing. We're going to go from the mean value theorem in section 4.2 all the way through section 5.2, where you find the approximate area by drawing rectangles and finding either a left sum or a right sum. Did you look over the sheet, or am I just making up examples?
The sheet.
I've got some examples. I got like an old test up here. I've got an old review sheet up here. That's what this is. There's no 4.2 on it, but maybe you have a 4.2 problem. Okay, so in section 4.2, the mean value theorem. Well, what does it refer to? Here's the picture. On a closed interval from A to B. There should be at least one number C at which the slope of the line through these 2 points is equal to the slope of the line through C. Does that help you remember it? For any continuous function defined on a closed interval where it has a nice smooth curve, so it has a derivative, there's at least one number C at which f of b minus f of a divided by b minus a, that's the slope of that pink dotted line, is equal to the slope of the pink solid line, which is f prime at c. So if f is continuous and differentiable, to B, then there is at least one number C in AB with slope of the tangent line equal to the slope of the line through the endpoints.
Recognize the formula.
So our job is to find it after we agree that the function that we have is continuous and has a derivative. So let's try explain why f of x is equal to the square root of 2x plus 1 satisfies the hypothesis of the mean value theorem on the interval, let's see, I gotta find nice, pretty numbers. 6, 7, 12. Then find C in the 4 to 12 guaranteed by this theorem. So I suppose my question to you is, would you know where a function is continuous and differentiable? Do you know what a square root function looks like? You can draw it with your finger, it's continuous, right? It's nice and smooth, so it's differentiable. We just have to make sure it's well defined on that interval. And the smallest value of x that I could use is the one that makes this stuff under here 0. So x is -1/2 is the endpoint. Any x bigger than -1/2 makes this function continuous and differentiable. All these x's are bigger than -1/2. Okay, so that's what we say. F is a smooth, continuous function on 412. Does it look something like that? Right, that's enough for me for it to explain. Okay, so what I want you to do is see if you can set up this little mean value theorem and see what equation it is that we're trying to solve. What does your f prime look like? What does f of 12 minus f of 4 divided by 12 minus 4 simplify to?
You know how for last exam you had you posted a review thing?
I think I have one posted. Have you not looked?
Oh, it.
I think I put it up there a few days ago.
Okay.
Pretty sure.
Yeah, that one was really helpful.
I mean, look and see if it's there.
Is
Is
this
it-
a paper one or is it?
It's on Blackboard.
Is it, or, what is it, like a video like last time?
Oh, no, I don't have that. I can look for that. Do you want that?
Yeah, the video was really.
Oh, okay. I'll look for the video. I think I've got that from last semester's class.
Yeah,
Okay,
I'll do both.
okay. I will look for that. Jeez.
Sorry for being high tone.
No, that's okay. I mean, I've got them somewhere. I've got them on YouTube. I just got to find the link. So in order to take the derivative, you have to write it like that, right? And then bring the power down, raise it to 1 power less, take the derivative of what's inside. So the 1/2 out front and the 2 out back will cancel each other, and I just have 2x plus 1 to the negative 1/2, which is the same as 1 over the 2x plus 1 to the positive 1/2. And maybe if I put it in a radical form, it might be easier to put that in an equation. So that's going to be on the left-hand side. I'll put a C in where the x is. Now we need the number on the right-hand side. So I'm going to go over here and I'm looking to find where 1 over the square root of 2c plus 1 is equal to. All right, so we need f of 12. We're putting a 12 in here. What's everybody getting for f of 12? 5? 2 times 12 is 24 plus 1 is 5. Minus f of 4, 3. And then we divide that by 12 minus 4. So the right-hand side simplifies to 2 over 8, which is 1/4. So we're going to try to dig that c out of there. So what I think I'm going to do is get rid of the fractions first by cross multiplying. And so my equation will look like 4 is equal to the square root of 2c plus 1. What would you like to do next? Square both sides. I get 16 is 2c plus 1. Subtract the 1. And then divide by 2. Good problem. I hope I can find them that easy on the test. Usually my numbers are much yuckier on the test, because I don't know how to work things out before I give them. 15/2 is 7.5, and that is indeed in there. So that means we did our algebra okay. Okay? All right. This is the review I worked on that video, so I think I won't work those same problems there. I'll work something differently. So the next thing we did in section 4.3 was all that stuff about using the first derivative to tell where a function is increasing and decreasing, using the second derivative to tell where the function is concave up and concave down, and then putting that together to give the picture.
This is 4.3.
This is 4.3. So for f of x is equal to, let's go with a 5th degree polynomial, 3x to the 5th minus 5x to the 4th plus 1. Find everything here. Want to know all the critical numbers? I want to know where it's increasing, decreasing, where it has a relative max, where it has a relative min, where it's concave up, where it's concave down, and I guess I should have asked for the inflection points first, but there are the inflection points there at the bottom. And then I want you to see if you can sketch a graph and put all that together. So I think I grabbed this out of a book so that it will in fact factor at every step of the way. Let's see if you guys can take it off. By the way. So look for the let's see, so that was last semester, it would be fall of 20. Let's see what day that was. November 17th. Three, okay. Where to go? Let's watch your video, Tuesday, November 17th. You know where I moved it? Okay. Okay, it's there. But the video that I put there goes through section 5.4. Your test only goes through section 5.2. If you want to study harder than you need to, that's fine with me too. You making any progress? I'm going to catch up a little bit just because we got the short class today. You kind of check as you see what I do. 15x to the 4th minus 20x cubed is the derivative. I got a common factor of x cubed and a 5, which leaves me 3x here, minus 4 there. So we have two critical numbers. 5x cubed is 0, and 3x minus 4 is 0. So this one's only when x is 0, and this is when 3x is 4, so x is 4 thirds. Those are your critical numbers, 0 and 4 thirds. So far, so good? Okay. Look at the sign of the derivative. Zero and 4 thirds. So let's see, -1 cubed is negative. Negative times negative is positive. 1 is positive, 1 is negative, so that's negative. 2 is positive, 2 is positive, so that's positive. So did you get it go up, down, up? So we write the increasing as minus infinity to 0 and 4 thirds to infinity. We write the decreasing as 0 to 4 thirds. It's like this around 0, so that means x is 0 gives you the relative max. It goes like that around 4 thirds, so 4 thirds gives you the min. Okay, so we need a second derivative. F prime is, was that 60? X cubed minus 60 x squared. So we have a 60x squared as a common factor with x minus 1 as the other. So there's two inflection points. 60x squared is 0 when x is 0. X minus 1 is 0 when x is 1. Quickly look at the sign of the second derivative around 0 and 1. Let's see, this is an x squared, so I'm not going to worry about that. That's always positive. A -1 in here makes that negative. A 1/2 in here makes that negative. And a 2 makes it positive. So I got concave down, concave up. Oops. Is that what you guys got? No? Yes. So it's only concave up to the right of 1. Concave down to the left of 0. Between 0 and 1. All right, let's see if we can make a graph out of this. Let's see, let's try to plot some easy points. F of 0 is 1. Oh gosh, f of 4 thirds, who cares? Yeah, I don't know what f of 4 thirds is. Let's find f of 1. 3 minus 5 is a -2, plus 1 is a -1. So I don't know if it's positive or negative at 4 thirds. I guess I got to plot it. Yeah. 3 times, what I'm saying, 4 thirds to the 5th, minus 5 times 4 thirds to the 4th, plus 1. Oh, gosh. Let's see, I'm going to have a 4 to the 5th. One of those 3's cancels as a 3 to the 4th. And let me write this as 5 times 4 to the 4th over 3 to the 4th plus 1. Oh, I don't know how big that is. I'm thinking it's positive. Positive something. Let's just call it star. Okay, let's put a graph in over here. So 0, 1 is here. And then 1, negative 1. Let's make this, I guess I'll make my scale bigger. Let's put 0, 1 there. And 1, negative 1 here. 4/3 is over here somewhere. 4/3 is 1 1/3, so let's put it here. And let's put it, I don't know, let's just put it here. And now I gotta make my arrows go up, down to 4/3. Okay, so it has to be down. So let's put 4/3 negative. Let's put it here. It's gonna go down, so it couldn't go down and pass through that point. So let's go down. And back up. That's what this tells me. And now, it's got to be concave down till I hit 0. It has to stay concave down till I hit 1. And then it has to be concave up everywhere. So I guess it looks like what you think it's going to look like, right? It should just look like a little x cubed kind of graph. That's concave down, that's concave down, and everything else is concave up. So nothing special. You probably want something special to happen on the test. You want a jiggly thing in there or a sharp corner or something like that.
I think the boring graphs have a special place. And in my,
They're very important to the basics.
Okay, who knows what the second derivative test says? What is the second derivative test?
tells us if it's a max or a min.
Tells us whether critical numbers are max or min by looking at the sign of the second derivative at the critical number. So I'm going to give you a function.
Is this still 4.3?
This is still 4.3. And so this is the second derivative test for relative extrema. So show that x is equal to pi is a critical number of the function f of x is equal to the cosine of x minus the secant of x. Then use the second derivative test to classify it as a relative max, a relative min, or neither. It's possible that a critical point might be the same as an inflection point, in which case it's usually neither. So, to show something's a critical number, you have to show that the first derivative at that point is 0. So just take the first derivative, plug in pi, and see if you get 0. If you don't get 0, I gotta know, because then it's not a critical number and doesn't do any good to test it. If you do get 0, then you take the second derivative, plug pi in for x, and the sign of the second derivative tells you whether you have a relative max or min. X is equal to pi is a critical number. Cosine of x minus the secant of x. Is everybody getting the first derivative of pi to be 0? Yes? Okay. So that means it's a critical number. Take the second derivative, plug it in, and then let us know what you get, relative max or relative min. Do you remember how to take the derivative of secant? Secant tangent. The derivative of cosine is minus the sine. We're plugging pi in for x. I know the sine of pi is 0, which makes the tangent of pi 0, because tangent has a sine in the numerator. And since it's multiplied by 0, I don't even have to know what the secant of pi is. I have 0 times that, and 0 here. So we have 0 minus 0, which is 0. That means it's a critical number. So now we're ready to take a second derivative. Bless you. The derivative of minus sine of x is minus cosine of x. How'd you take the derivative here? Product rule. So don't lose the minus sign. Let's put that out in front of parentheses so I can put my product rule in there. So it's the first times the derivative of the second. What's the derivative of tangent? Secant squared plus the second times the derivative of the first, and the first was a secant, so we should get a secant x tangent of x. So you can simplify that if you want. I don't. I'm just going to put the pi in for x. F double prime at pi is minus cosine of pi. I'm going to distribute the minus sign here. I guess I'll go ahead and simplify and make that a secant cubed of pi. Plus, minus, I said I'm distributing it. The tangent of pi times tangent squared of pi times the secant of pi. But remember, the tangent of pi was 0, so tangent squared is going to be 0. So that term back there is 0. The cosine of pi and the secant of pi are going to be the same number since secant is 1 over cosine. Who wants to take a shot at what the cosine of pi is? -1. So here I get a -1. Here I get a -1 cubed. Back here I get 0. So that makes that a +1. -1 cubed is -1. That'll make it a +1. So I get a positive number. All right, what happens if the second derivative is positive? We have a minimum, right? Minimum at x is equal to pi. Do stuff like that? Good. Okay, so that's 4.3. In section 4.4, we looked at rational functions, and we identified where they have vertical and horizontal asymptotes. The vertical asymptotes were where the denominator of the fraction was 0. Horizontal asymptote was, we took the limit to infinity. Usually we just looked at where the degree was. If it's bottom heavy in terms of higher degree, what's the horizontal asymptote? No, that's not if it's bottom heavy. Bigger power on the bottom, the horizontal asymptote is 0. If the same powers, then you look at the ratio of the coefficients. If it has higher power on top, then there's not a horizontal asymptote. We can describe the behavior of the function near the asymptote with limits. So this is 4.4. IdenTIDENTIFY, the horizontal asymptote, vertical asymptotes of f of x is equal to x squared divided by 9 minus x squared. Please say it again.
On the exam, are you ever gonna ask for like the diagonal?
No, I won't ask for a slant asymptote, just the two basic ones. Okay, so like I said, the vertical asymptotes are the values of x that make this thing undefined. You got any? Or is this not defined? And? 3 and? Negative 3. So we have two vertical asymptotes. They're equations of lines, so make sure you include the x. We have the vertical asymptotes at x is equal to 3 and x is equal to negative 3. What about the horizontal asymptote? And again, it's an equation of a line, and it's a horizontal line, so it's the line y is equal to negative 1. Okay. So what if I ask you this? What is the behavior of this function when x is near that vertical asymptote, but say on the left of 3? And what is the behavior of that function when x goes to 3 from the right? Yes?
How did you find horizontal asymptotes?
We looked at, so you have the same degree, so you just take the ratio of the coefficients. Positive 1 here, negative 1 there. That's what we do when we take the limit to infinity. Now, without a graph, you really can't tell what this function's doing to the left and the right of 3. So you can fake a graph by plotting some points, or you can take a derivative and look where it's increasing or decreasing, whichever you feel quickest at. Maybe we'll try plotting points. So here's roughly what we got. We've got a function that does, let's see, 3 and negative 3. So there's negative 3. There's 3. And then we've got the horizontal asymptote at y is negative 1. So I have like 6 regions to look at. Over here, if the graph is up here, it stays up here. Or if it's down here, it stays down there. So really all I'm going to do is plug a number in and see where it is. Like what happens if you put, say, a negative 4 in for x? A negative 4 in here and a negative 4 in there. When x is negative 4, I get 16 on top, 9 minus 16 on bottom. 9 minus 16 is 7. So I have 16 divided by negative 7, which makes it negative 2-ish. So I'm thinking it's down here. And I said if it's down here, it's going to stay down here. So it's going to do that. Now we're up here. It's either in here or in here. So let's plot x is 0 and see what happens. Where's the graph when x is 0? Zero. Oh, I lied. Could possibly go down and up. So maybe I should plot at another point. Let's plot x is negative 1. So when x is negative 1, I get a positive 1 here and a 9 minus 1 there. So I get a 1/8. So it's going up over here. And since those powers are even, it's symmetric. So it's going up over there. Right? Even functions are symmetric about the y-axis. And so that means, right, since it's an even function, this has to be symmetric to that. So I think I got the picture. And now I can answer my question about the one-sided limits. So put your eyes on the line x is equal to 3, and look slightly to the left of that and tell me where the graph is going. It's this piece right here you're describing. It's going to plus infinity. Your vertical asymptote, your limit is either plus infinity or minus infinity. And if you're on the right-hand side of that line, negative infinity. And then we can ask the same thing over here. This one says that as x goes to negative 3 from the left, the y values go to minus infinity. This says as x goes to negative 3 from the right, the y values go to plus infinity. So a quick graph, however quick you need it, can answer the one-sided limits around the vertical asymptotes. Or a derivative will do the same, but I just thought a derivative would take a while here. Okay, so that was section 4.4. .5 was L'Hopital's rule. So let's see if you know L'Hopital's rule. What is the limit as x goes to 1 of the inverse tangent of x minus pi over 4 divided by the tangent of pi over 4x minus 1. So you need to know two things here. You need to know what the tangent of 1 is. I'm sorry, the inverse tangent of 1, and you need to know what the inverse tangent of, you need to know the inverse tangent of 1 and the tangent of pi over 4. If you know one of those, do you know the other one? What's the tangent of pi over 4? Tangent of pi over 4 is 1, so the inverse tangent of 1 is pi over 4. So this says pi over 4 minus pi over 4, and the bottom says 1 minus 1. So it has the form of 0 divided by 0. That's your cue to use L'Hopital's rule, which says derivative of the top divided by the derivative of the bottom. Don't be doing anybody's quotient rule. Derivative of the top divided by the derivative of the bottom. Then see if you can get the limit. So, do you remember the derivative of the inverse tangent? 1 over x squared plus 1. I got this way off screen again. All right, so you get 1 over x squared plus 1. The derivative of pi over 4 on top is 0. Now we need the derivative of the tangent of pi over 4x. What's the derivative of tangent? Secant squared. So we get secant squared of pi over 4x times the derivative inside. The derivative inside gives me a pi over 4. And then the derivative of that one is 0. So now we're putting 1 in for x. A 1 here gives me a 1/2 in the numerator. Okay. A 1 here is asking you to find the secant of pi over 4, which is 1 over the cosine of pi over 4. 2 over the square root of 2. Now square it. 2 over the square root of 2 all squared. And so there's the half on top. Pi over 4. 4 over 2 is 2. And so I have 1/2 divided by pi over 2. 1/2 divided by pi over 2, which is 2 over pi. And so our limit is 1 over pi. If we keep getting 0 over 0 or infinity over infinity, we do more. But then we have other indeterminate forms, like infinity minus infinity, 0 times infinity, and then the exponential indeterminate forms. So let's quickly do an exponential one. It's going to go to infinity. Let's look at this one. 1 plus 1 over x, all raised to the x squared power. So the numerator is going to infinity, the power, and the stuff in the parentheses is going to 1. So this describes something of the form 1 to the infinity. Remember what to do? Use a logarithm. So we call this limit L, and we take the natural log of both sides, which brings this power down in front of the logarithm. So we have an x squared times the natural log of this expression, the natural log of L. Now as x goes to infinity, this x goes to infinity, that goes to 0, so this goes to the log of 1. We have another indeterminate form, infinity times 0. What do we do with that?
X squared in the denominator.
Put the reciprocal of x squared in the denominator. Now it has the right form to use L'Hopital's rule. We have 0 over 0. So now we do L'Hopital's rule. The derivative of the top is a logarithm. So it's 1 over u times u prime. One over u gives me a 1 over 1 plus 1 over x. Now I'm in the parentheses. The derivative of that 1 is 0. What's the derivative of 1 over x? Negative 1 over x squared. So what's the derivative of 1 over x squared?
Negative 1 over x to the 4.
Well, think of that as x to the negative 2. So you get negative 2, x to the negative 3, which is negative 2 over x cubed. Okay, so let me see how I'm going to simplify this and make it fit on the board. I'm going to put the negative 1 over x squared on top of the 1 plus 1 over x. Then I'm going to take this and flip it over and multiply it like that. So where's it come out? Okay, be that way. Okay, so I put these next to one another because that's where I'm going to cancel. The negatives cancel. This x squared goes into that x cubed, and it leaves me an x. So the negatives are gone, and I'm going to have x over 2 divided by 1 plus 1 over x. Right? Okay, well, that's not indeterminate form anymore. As x goes to infinity, so does that. As x goes to infinity, that goes to 0. So I have infinity divided by 1, which is infinity, right? That's the natural log of L. So L is e to the infinity, which is infinity. So this limit doesn't exist. Sorry, I made it go quick. But usually something like that gives you equal power. So look those over. Okay, what else? What else? That's 4.5. 4.6 were word problems. So what I did is I put 2 word problems on there, just like I did with related rates. You can do the extra one for bonus, but pick one of the 2 and do it. We've seen things that had area, perimeter, surface area, volume, the distance rate times time ones. That's pretty much all of them. And then in chapter 5, the basic integrals. I gave you a problem where you had to figure out what C was with each step with velocity and acceleration stuff. And then I drew a graph and said use n is equal to 4 rectangles to approximate the area, use a left sum and a right sum. Good? Okay. I got a practice sheet on Blackboard, and I just now hooked up the video from last semester on Blackboard's review. But remember, last semester we had 2 sections beyond here, so stop at 5.2. And I'll see you later. Right here. If you need extra time, I'll let you bleed over because my next class has a test too, and you guys can just stay and keep working. But if you have a next class, I'll try to get here Monday at about 11:30 if you want to start a little bit early.
I figured out I don't have a class after my class starts. So
Then I guess I have to get here at 11:30? I can finish my workout in the morning? Okay, then I won't be here at 11:30. We'll just come here at 12 and we'll take our test.
thank you.
No trip. Thank you.